Welcome to this new video where I'm going to be talking about singular value decomposition, or SVD as the people say. And I think SVD is a very cool topic. It's super popular but very confusing, as you can see by these images. But at the end of this video, I think you're going to be able to genuinely understand what is going on, what the story of it is, and how to compute it. I don't think that's too hard, but actually, like, what is going on here? What do these images mean? I think by the end of this video, you should be able to understand that if I do my job. Okay, so what am I going to talk about in this video? Well, okay, this is a long list, and I think the reason SVD is important and fun, like very satisfying once you understand, is because it requires you to have a decent understanding of basically like all the core topics of linear algebra. So if you have a decent understanding of all of these core topics, then you will pretty easily understand SVD. But it's hard to juggle all of these ideas in your head, so that's why I'm going to go through all of them slowly and just writing down in this nice whiteboard space and building all up the knowledge to get to SVD. Because you can find a bunch of YouTube videos where you just learn how to calculate or take the decomposition, but that doesn't help you at all. Like a computer can just do that. The point is to actually understand why and what's going on. So my main reason for why I think SVD is this nice combination of topics, but there are plenty of examples of it actually being useful to do machine learning or other things that you should just look up. Okay, so this journey begins with linear transformations. So if you're clicking on this video, you probably have taken a linear algebra class, so I think I'm going to go quicker through the first topics, but they are super important. So we're going to start super simple. In linear algebra, you're always talking about matrices and vectors. So there's the way of writing a matrix like this, right? That's how you see it written down on paper. But more importantly, you want to think of a matrix as a function that does something to a vector. So people write vectors like this. So you want to start drawing graphs as soon as possible when you're doing linear algebra and trying to learn intuition. So this is what visually V looks like as a vector on the 2D plane. And so a matrix looks like this, obviously, but we want to understand now as we're doing things visually, what does that look like? And that is kind of the idea of linear transformations, is what does this matrix mean? And so this matrix is a weird transformation, but let's do this matrix. This matrix will scale it will scale a vector like this. Okay, so if this is B, so now this is new V. So if this is the matrix B, B times V equals new V. And then it changes how it looks. Now new V is like this. So that is a linear transformation, and that word basically means transforming a vector, and it does something visually. Okay, so that is what B looks like, and then maybe you could do 1, 1, 1, 0, and it's like it's a shear. So instead of like at a nice angle, I think it will go like this or something. Honestly, I don't know, but it will change v. That's kind of the whole point here. Okay, so that is a linear transformation. A matrix will transform a vector. So there's a couple different types of matrices that people will talk about in linear algebra. There's a square one, like we just saw, and like a long one, or a fat one. And these are interesting as well. And what I mean by long and fat is more rows and columns and more columns than rows. That's what I meant. Okay, cool. So this type of matrix, this square matrix, in a lot of scenarios will just move the vector. But the point of linear algebra is that you're always talking about in not just 2 dimensions, but in many, many dimensions. So we're going to talk about the idea of rank of a matrix. And this is going to be kind of hard by just drawing it. You can totally look up a video and come back with a better understanding maybe, but I'm going to give it my best shot because we like to stick to the whiteboard. Okay, so let's see. So there are many different matrices that you'll come across, and some of them, when they transform a vector, they'll mess with the dimensions. So here is two dimensions, but then after you apply A, the matrix, as a linear transformation, it's possible that it squishes everything into 1 dimension. So what does this kind of A look like? And I believe it looks like this, like this. I think. Okay, let's test it. So if we had 1, 2, then this would result in 1, 0. Yes, I think so. Okay, so there are matrices that will squish everything and it will change the dimensions. It could go from 3D to 1D, or it could go from 3D to 2D. It can, anything to anything. And when something changes the dimensions, especially it shrinks the dimensions, that means something about the matrix. And the main thing that you have to know is that when something shrinks it, that means that it does not have full rank, is what it's called. Full rank. And that also means that the determinant, not full rank. And then the determinant equals 0. So yeah, I'm going to be going a little bit quicker through these topics. Not full rank, and then the determinant is 0 because it's squishing space. And it's kind of being weird. So this can happen with both types, square and rectangular. With rectangular, it's like almost bound to happen because the columns are not linearly independent. Which means that so let's see, linear independence. We already kind of covered stuff like this. Okay, so we have a vector v, and then we have a vector p. These two vectors, with any combination of these, if you rotated them and scaled them and you rotate them, they would fill up the whole 2D space. because you can just like rotate and scale them, and then they just like fill up the whole plane here. But if you had three dimensions, you had V and you had P, you would have no chance of filling up the 3D space because there's only two vectors. And so there's like a lot of different examples that you can have like this. Like you could, if you moved it a little bit and then scaled it, like you wouldn't be doing much. You wouldn't be able to fill the 3D space. So if you had three vectors, you would. And so if these three vectors are put inside of a matrix, P, V, and C, then this has full rank, and these are all linearly independent. So if the number of vectors equals the number of dimensions, or the number of columns, or the number of dimensions like in your drawing, then there's full rank, and you can span the whole space. Okie doke. So that is what like a linear transformation is, and then like all of the kind of different types of matrices and how they can have different types of transformations and results from the transformation, how they can change vectors in the spaces that they live in. Okay, so let's move on to, we talked about a little bit of determinant, linear independence, and linear transformations. Okay, so now we get to talk about eigenvectors, which is probably one of the most important parts here, and very popular too. Okay, so an eigenvector. So we have a matrix that does some linear transformation. It moves a vector somehow, and it can move, if you think about all of the vectors in space, it will move all of those vectors somehow. So this is V. So if I applied V, if I applied A to V, so it's like, all right, I'm gonna A this, then it would do something, right? But you could also think about, you have like every vector in this whole space, like every possible vector that you could draw. What is the result of A'ing this whole thing? And you would basically just end up like changing the coordinate space. You just like shift the whole coordinate space and somehow. And that is the essence of a linear transformation. And like I said before, if you went from a 2D plane to just a 1D, then that is a specific kind of linear transformation, and that is one with determinant 0, and where you're shrinking things onto a new dimension. And that matrix that you use, maybe it was B, will not have full rank. Okay, so that's a good summary. So then how does this relate to eigenvectors? So when you have some space, and now instead of just thinking about like one vector, we're going to think about like all the possible vectors that exist in this space. And this doesn't have to be for 2D, this is for everything. So all the possible vectors, what happens when I apply C to this space? The whole thing is going to change somehow. And let's say I scaled everything by 2. So that's this matrix. Right, as an example, with just one vector, let's do 3, 3. The new vector here is just 6, 6, right? There's a scaling everything, so any possible vector that you apply to this matrix is going to be scaled by 2. So that means, that's a terrible drawing, so that means that any vector here will grow by 2. And this vector will grow by 2. Right? Okay. So when we apply this C matrix, this is not a good example. And you'll see why in a second. Okay. So instead of that example, we're going to do 2. when I apply this D matrix, when I D this, only some vectors, so most vectors will change like we did last time. Most vectors will have, like, they'll grow or they'll change the angle or something. They'll change in some way when you D them. But there are some vectors for this matrix specifically that do not change, in the sense that they don't change their angle. So let's see. So like this would be an example of changing your angle, right? You would rotate like this. Instead, there are some vectors that only grow. And this is why it was a bad example, because we were interested in the ones that only scale, right? They can go from here to here, right? That's a negative scaling. Or they can go from just longer, they can go shorter, you know. These vectors only scale, they don't change the angle at all. They don't rotate at all. So these vectors are called eigenvectors. So conceptually, it's not that hard, right? You're doing a transformation, and you're finding the vectors that don't rotate. They only scale. So then this kind of has this idea is summarized in this formula. So you're Aing this x vector, and that's the same as just scaling by this lambda. So the lambda could just be 2. It's just a scalar. So you're scaling by 2. So in this first example, for almost, I mean, it was kind of any vector, but any vector, applying A was the same as just scaling it by 2. And so when you're asking for eigenvectors, you're looking for all vectors x that satisfy this. So there's a way to calculate this, which I think is less important, but we can go through a little bit here. Okay. Right, so this is what it looks like. And you do that by basically ax minus lambda x equals 0. And then you factor out the x like this. Okay. Nice. So then here, this is a new matrix. This is a brand new matrix that we're going to talk about. But by satisfying this equation since solving for x, then you can know all of the eigenvectors. But we kind of have a problem where we don't know that yet. Like we could just guess, like we could verify, like, okay, if we had 2 as an example, like, okay, we can plug it in here and then solve for x. But we have 2 unknown variables, which is a problem. So instead, we want to solve the determinant of this, where that equals 0. Because like I said before, this is solving for all of the lambdas that will turn turn this matrix into a transformation that squishes things and changes the dimension. It's hard to write that down, but that's how we're gonna visualize it. Okay, so you can solve this equation because this is confusing looking, but it's just a matrix, right? It's going to be like 1 minus lambda, or let's say like 2 minus lambda, 0, 0, 1 minus lambda. Like that's the matrix that we had before. And then you want to get where the determinant equals 0. So then you can solve that, and then it would be like 2 and 1 are the lambdas that we're interested in. So these are our eigenvalues. And these is by how much do the vectors scale. So we wanted to find the vectors that do scale, but these are telling us by how much. Some vectors will be 2, some vectors will be 1. So then to get the vectors, you reconstruct the matrix like this. It's kind of weird looking. This is for lambda equals 2. And then you solve this equation. And that gives you all of the vectors. So there are many vectors, right, for everything, because like this would grow a little bit, and this one would grow, and this one would grow, but they're all in the same direction. They all share the same span of that line. Okay, so that is eigenvectors and eigenvalues. That is how to find them and what they mean. Right, they are like this core property of a matrix, and but more importantly, like they're like this core way to describe a linear transformation. Because if you can find, so let's say we have a linear transformation where like all of the vectors, it kind of looks like this. I don't know, things are like moving in that direction a little bit, but there is one vector that kind of like stays the same every time in this direction. That's really important. Like this line is really important. We want to keep track of that for a specific linear transformation. And we'll see why in a second when we move on. Okay, so let's pin linear transformation, or pin eigenvectors for a second. And now we need to talk about change of basis. This is a little hard for me personally. Okay, so we talked about linear transformations and how they kind of like describe like changing all of the vectors in a space somehow. But that and then you can just write down a matrix to do that linear transformation. But these numbers are making an assumption that the coordinate system is like 1, 0, and they're 90 degrees, and this is the x, and this is the y. It's making like an assumption, and you may not necessarily want this assumption. There are times where using a different coordinate system is easier, and you're like, that's gotta be a lie. That new coordinate system is never going to be easier, but you'll be surprised because that's a big part of SVD. Okay, so this linear transformation is taking an input within our standard basis that we all already know. This is 1 and this is 1, and these are the standard vectors, right? So if I did 1, 0, that's this, and then if I did 0, 1, that's this. That's the standard basis system, and then the x and y lines are 90 degrees, and it's like normal. So we're inputting a standard basis, something that's in our language, the standard basis, and we're outputting something in our standard basis. Right? And the numbers are in standard basis. But what if I came up with my own basis, my own language essentially, and I said that this is 1 and this is 1, which is supposed to be longer than the ones up here. And let's say like what is like, how would you describe this in our language? How would you translate from our language to this language? That is kind of the idea of change of basis. So the point of there are a couple tools you have to do change of basis. The first one is called the change of basis vector, which is named matrix, which is named super well. So the change of basis matrix, you put in the standard basis vectors in our language. Okay, our language. So this might be like 2, 3, and 1, 2. I don't know. That's kind of what I think these look like if we were to like overlay our standard basis and see what these vectors are. Not quite, but you see what I mean. Okay, so this is the change of basis matrix. And so this takes as input something in our language, standard basis. And let me double check. The foreign language, and outputs it into our language, I think. Yeah. Okay, so then there's also the inverse, which reverses this. We input something in our language, and it will output what that represents in the foreign language of the other like basis. So these two tools are super important. Change of basis matrix and the inverse of the change of basis matrix. And I always get confused what is the output of them, but the idea is important. You put in the basis vectors in our language of the new basis, and then that allows you to translate. Okay, so now we're going to combine everything and talk about diagonalization. And if you understand diagonalization, then SVD is super easy. Okay. So, diagonalization. So diagonalization is one decomposition. So we're already close to SVD because we're doing one of the words. So a decomposition is when you break down a matrix into other parts. And I'm going to write down what we're going to work up to in a second. But I want to show that is breaking it down into multiple parts. And these parts are other matrices. And the reason this is useful is because you can use these other matrices easier than you can just use A. Okay, so the way you do this is reliant on finding eigenvectors and eigenvalues, actually. So I can kind of just tell you that this is made up of eigenvectors, this is made up of eigenvalues, and then this is just the inverse. So you only need to compute these two, put them together, and that gets you a decomposition. But the reason this relates to what we've been talking about is because each of these vectors individually are important. Okay, so if I were going to multiply a vector by this, so we can either do A times a vector, which will do a transformation on X. We can either do that, or we can do this, because these are A and this are the same. Right, so what happens if I do that? So this is like split up like semantically. So P inverse, this does something specific. So like we talked about before, this is actually a change of basis matrix. So P inverse will take something from our language and convert it into the new language. But this new language isn't arbitrary like I've been talking about. The new language is made up of a basis of eigenvectors. Okay, what does that mean? A basis of eigenvectors. So, before, we talked about how a matrix can have many eigenvectors. And so a matrix can have many eigenvectors, right? That means that there are like essentially multiple lines which do not move. Lines made up of many vectors which do not move when it gets transformed. All these lines will not move. So this is number 1, this is number 2, and these span the 2D space. So I could just select this one right here is V, and this one right here is P, and like we saw before, any combination of these two vectors will span the space. If I just had V, it wouldn't span the space because it's only going to span this line, right? Does that make sense? You can only go like up and down this line. You're stuck on this line. But if I give you a new degree of freedom, P, or P and its brothers, then you span the whole thing. And so if these are eigenvectors, or P and V are eigenvectors, and they span the whole space, that is an eigenbasis, right? You pick V and P to be to be your basis vectors. So V and P are now I've chosen them to be basis vectors, and now they're basis vectors of my eigenbasis. They are the foundation of my new language in this basis. Okay. W. Good. So this is good progress. So this is essentially made up of those basis vectors, right? But it's the inverse. So that means it's translating from our language. So x, like we're going to have an input vector in our language, and then we're going to convert it to that new language, which is made up of the eigenbasis. And the reason this is useful is because D is a super simple vector. It's going to look like this. It's called a diagonal vector. And this is a super simple matrix. And so we are going to scale whatever the result of this is. So when we apply D to this, we're only doing a scale, which is a super easy transformation. It's easy to compute. It's easy to look at. I like looking at this matrix. So when we apply D, that's super easy. We're only doing a scale because we're converting it to a new language. So in this at this time, we're like in the eigenlanguage, or the eigenbasis, eigenlang. And then it's a super easy transformation. And then P will reach, or let's say like translate back into standard lang, right? Just like we talked about before here with the change of basis matrix. So we could have done the transformation with A, but it might have been like some ugly looking matrix. So we broke A up into 3 parts, and then we can basically have a much simpler transformation of D, which is guaranteed to look, I don't know, maybe it's like guaranteed to look like this. It's guaranteed to be diagonal if A is diagonalizable. Cool. So that is how you relate change of basis and how you relate change of basis to decomposition. Okay, so then this is like 90% of SVD. SVD is basically just a new trick on top of this diagonalization idea. So you build on top of that, and we finally made it to SVD. First, let me just go back to what we had before. Right. So this is great. This is a great tool, and we're really almost there. But the problem with this, so there's a couple of problems, is that a needs to basically be square, and a couple other things, and it needs to be diagonalizable, which means like there needs to be an equation such that this works, which may not be true. And we want to be able to use our trick to do good transformations and easy transformations on any matrix. And that is the problem that SVD solves. So to show you that, first let me write something down. A transpose A. So I think you can maybe see where this is going, but we're going to start with this, and then we're going to be able to see what SVD does. Okay, so A transpose A equals PDP inverse transpose PDP inverse, right? Because I'm just plugging in what we had before, because we liked that equation. So this equals okay, so just trust me on this one. There are some weird things I'm doing here, and that is kind of because this is very similar to this. So honestly, it doesn't necessarily matter, but we're gonna do this. Okay. Great. So PD, and this becomes the identity because that is like basically the same as the inverse. So we have D. Oops. Great. DTD and this. Okay. So then now, this is something new, essentially. This is P, DT, D, PPT. But this is a new matrix called sigma. And you will recognize that from the SVD equation. And that is the same as D, but with all of the eigenvalues squared. So if this was my D, then my sigma would be 3 squared and 2 squared. It's still diagonal like D is, like this. So that is the new sigma. So now we know one of the three things in SVD. And the reason these are both P instead of U and V is just because we used the diagonalization equation when we could instead use the SVD. Okay, so when you do that, that turns out into U sigma V transpose, because the U's and V's just follow along. Okay, cool. So that is the singular value decomposition. These are the three different things that decompose, but these are like there's no problem with thinking about these three things as the exact same function as these three things that we had before, PDP inverse. They're basically doing the same thing. They're more powerful because of the different types of matrices, and you can have non-square matrices, and it makes things more complicated, but it's like the same idea with change of basis and transformations. Yeah, so now we can go back to these images, wherever they are. There we go, and see how this works. So these are differently shaped because A can be a non-square matrix, but we now know what each of these three matrices are and that they are even matrices in this decomposition. And then this is so complicated, but we literally just talked about that too. So here, we could do a transformation with A, but A is probably gnarly and ugly. So instead we break it down into three components, and then apply them one after the other. So VT first translates into the new language, or in the eigenbasis. Sigma scales. Sigma is the nice diagonal matrix that looks like this, that we like working with. That does some sort of scaling. And then U translates it back into the business that we like of the standard basis. So that is the singular value decomposition. Thanks for watching. I hope this was helpful. It was a little rough around the edges, but I think that is a good tour of linear algebra. And if you know singular value decomposition, you know linear algebra. So it was a good tour of linear algebra, and basically how these two graphs or images are related, because that's kind of the essence of this whole thing. Boom. Good night.